So now a couple of examples, and the first of them, of course, is a potential. The classical example: what if L epsilon is a multiplication by a compactly supported potential? Then we just see that K epsilon is equals to. So, and once again, I shall rewrite this formula in the following form. So this is in view how A0 acts. This is just the integral, the mean value of this function over the real line, plus P epsilon squared plus epsilon squared. So if L epsilon is a potential, then there is one eigenvalue, there is one K which solves this equation, and K epsilon, so I get here minus, it seems that this is wrong. Okay, but doesn't matter. So it's, then we shall get here something like this. It seems that there should be minus here in U of x. So нет, отрицательный. No, it's fine. So this is the solution to our equation, which I had here, I mean this one. And when I know for this K epsilon, I have a function f epsilon, which can be found like this. And here I should put also my root of this equation. When I check this f epsilon, then I recover the function psi, and this function psi actually solves my eigenvalue equation. The only question is how this function behaves at infinity. Because we know that, so this psi is actually, so this is the action of the operator A of k. So it means that we should apply this operator to our f epsilon, and then we shall get the corresponding u of psi, and at infinity this function behaves like this. So my psi behaves like this. And now I see that if the real part of k is positive, then this function decays exponentially at infinity. So if the real part of k epsilon is positive, then the function psi, then psi epsilon decays exponentially. And if this is not the case, if it's negative, then it grows exponentially. So if we want to think only about the eigenvalues, then apart of solving this equation, we should also take the real part of its root. So we should choose only the case when the real part of this K epsilon is positive. Then we shall get the eigenvalue. If it's negative, then the corresponding solution of this equation grows exponentially. And this is also a nice case. This is a resonance. It means that if the sign of the real part is positive, then we get eigenvalue. If it's negative, then this is a resonance. Depending on the sign of this root, of the real part of this root, we either get eigenvalue or resonance. So we in any case, we get a spectral object. But the nature of this object depends on how the corresponding non-zero solution behaves at infinity. And actually, in view of our calculations, it's determined by the sign of the real part of the root. So it means that, so to have it positive, the potential, the mean value of the potential should be negative. So how to check that the real part is positive? It's sufficient to have that the real part of the leading term in the asymptotics for K epsilon is positive. It means that this integral should be negative. It means that this integral should be negative. So if the mean value of v of x is negative, then I have an eigenvalue. If it's positive, then I have a resonance. And both the eigenvalue and I have either eigenvalue or resonance, not both of them, just one of them. It's also possible to deal with the case when the real part is 0. What one should do in this case is just to find the next term in this expansion, just that equation. So when you write here the Neumann series, take not only one, but also the next term, minus epsilon L epsilon A1. And then it's possible also to find the next term here. And then if we cannot decide with the real part of or the first term, then just work with the real part or the next term. For instance, if here I have 0, and I cannot understand whether it grows exponentially or decays exponentially, it's also possible to take the next term in this expansion, and then take the real part of this, the sign of the real part of this next term. And this is a classical example, and a less classical example is when, say, L epsilon is the second order differential operator of this form. So what is the way of dealing with this example? So just act by this operator on 1. L epsilon on 1 will be, all these terms are not important. So when the derivative acts on 1, then it's 0, and we have again a 0. Actually, having here the second order differential operator, we get exactly the same picture as in this example. So these two terms are not really important. It will be again the mean value of the potential. And then, of course, when the answer is the same. The next example is this integral operator. When it works like this, what we should do, we should substitute here 1 and then take the mean value. So finally, the leading term for k epsilon will be, how it will be, minus epsilon integral over, it seems that I forgotten here half, because there was 1/2 in A0. So here it will be also half, and here it will be over r squared kxt dx dt. For the integral operator, the leading term will be this full mean value of the k of this function in the integral, and again then we should take the real part of this integral, the sign of the real part. A much more nice example is comes from the point that L can depend also on epsilon. Because here we have here just a very simple example, so that L epsilon was independent actually on V. A very nice example can be created once we let L epsilon be exponent in the power I over epsilon V of x. It's bounded. It doesn't matter that I have here 1 over epsilon. It's your imaginary exponent, and it's bounded by 1. So all my assumption on L epsilon work, why not? And what is the asymptotic for the k epsilon? It will be minus half. Actually the same as here, but with this exponent. And now I should take the sign of the real part. Of the real part or the first term. So this real part will be minus 1/2. I don't care about this epsilon, it's positive. The real part of this exponent will be cosine 1 over epsilon, and this integral. Just imagine that this one is non-zero. And it even doesn't matter whether it's positive or not, because when epsilon goes to 0, this cosine goes up and below the 0, and it has either plus or minus, and it means that in the vicinity of the bottom of the spectrum, I have resonance eigenvalue. So, and small epsilon is, the faster this process goes. So for a very small epsilon, I just change the nature of this object very quickly. And this is where, at least this example can explain why self-adjoint cases are, in a sense, more interesting or more richer than the self-adjoint one. I can imagine, I can have an emergent object, but the nature of this object can change very quickly. So for some epsilon, it's resonance. For some epsilon, it's negative. It's an eigenvalue. And okay, so all these things are possible. And now I want to pay a little bit more attention to the main steps in whole this technique. Actually, there are just two main steps, and the first of them is solving this equation. So actually, what we need to have, we should have a resolvent for the limiting eigenvalue. We should know the behavior of a resolvent for the unperturbed operator. Actually, we need to have a formula something like this. And here we began from assuming that K is positive, or real part of K is positive, when I said that K is complex. It means that we should make a meromorphic continuation of a resolvent in the vicinity of the edge. So this is the first point. Actually, this continuation was made here when I said here that since F is of compact is compactly supported, then I can think that K is complex valued, and all this formula is still well defined. This is the step where I made the meromorphic continuation of the resolvent. And once I have this continuation, I should know how this continuation behaves in the vicinity of the edge of a spectrum, namely for K close to 0. In my case, it was the pole. This resolvent had a pole. Once we know how this free resolvent works, then we do all this stuff, and finally what we have here is the following equation. And as you remember, this pole then came up here. So actually, if here I shall have 1 over K, it means that then this K will finally come here, and it will be equal to epsilon. For instance, if I have here something like phi of K, say for some more complicated model, then of course I shall get here phi of K. And this is actually the main point, that we should make the meromorphic continuation of the resolvent. It has some, for instance, it has some pole there. When we turn on the perturbation, and then this pole moves. And for the moving of the pole, for this new pole, we have some equation. And actually, what we should do that is to find the 0 of some analytic function in K. And by the way, it's at least in all examples I shall discuss, it's quite easy to study rigorously this equation. For instance, this can be done either by Rouchet theorem or the theorem on implicit function theorem, something like this. So, but the main point is that for the unperturbed operator, we should know the structure of a meromorphic continuation of a resolvent. And also this one here, which appeared, it's not just by chance. It's not just that it just happened. One is a very important function here, namely, if we consider the unperturbed operator, which was just the second derivative. If I put here 1, I shall get here 0, 1, right? it means that at the bottom of essential spectrum, I have a virtual level. And this one is exactly this virtual state which corresponds to this edge. And finally, actually, what I shall get is that the perturbation will act on this on such states, and then some expressions in terms of such action will then appear in this function f epsilon, and here I shall have the same function as I had here. So this is the main thing, and actually what we did since the first paper by Gadich in 2002 is that this idea, this simple technique was applied to plenty of models. And in some models, the results were very similar actually to this one-dimensional model. But in some models, the results were unexpectedly completely different. And for instance, this happens if we go to a two-dimensional case. Then today I shall show like a model of a waveguide which we studied, and where this technique actually works without any changes, almost without any change. The only point is that the meromorphic continuation is a bit different. Namely, we consider a waveguide, a planar waveguide. This is a strip of width pi. Here I have x1, here I have x2, here I have minus L. The operator is just a Laplacian, and this is and here I have a combinations of the following boundary conditions. So this is a self-adjoint operator, and the perturbation in this model is this Neumann window. So I have first a waveguide with a pure Dirichlet condition, and then on a finite segment, I change it to the Neumann one. The question how this influences the spectrum of such operator. The first point, which can be the first thing which can be set from the very beginning, is that the essential spectrum of this operator is 1 plus infinity. So I again have a half line, which is the essential spectrum. Once the Neumann window appears, then I have additional eigenvalues. So the point is that if there is no Neumann window, just the first boundary condition and the first when L is 0, then the spectrum is just the essential spectrum, and this is this half line, and actually this is how it looks like. There is nothing else. As soon as L is greater than 0, no matter how it small is, I have at least one eigenvalue below. For positive L, the point spectrum of HL is non-empty. Once we add a Neumann window, it doesn't matter how big it is. Immediately we shall have at least one eigenvalue. And the situation is so how it happens? The situation is so that there are some critical values of this window. They exist numbers lambda 1, L1, L2, L3, etc., Ln. So these are critical values of the length of the size of this Neumann window, such that the number of the eigenvalues in the point spectrum equals exactly to n, as L ranges from Ln plus 1 up to Ln plus 1. So when L is 0, we have nothing. We have no eigenvalues. When L is positive and small, we have just one eigenvalue. Then we make this size of this Neumann window larger and larger. And then at some point, namely once L is greater than L2, I shall get one more eigenvalue. Namely, the first eigenvalue which appears immediately, it goes to the left. When L becomes greater and greater, at some point the first eigenvalue is here, and then there appear one more eigenvalue. When I make it wider, at some point I shall get the third eigenvalue, etc., etc. So if the width of this Neumann window is very big, then I can have as many eigenvalues as I want. So the picture is so that from time to time they emerge one more eigenvalue from the essential spectrum. And the point where this happens, it can be described as follows. So in order to have such emergent eigenvalue, we should have a virtual level at the bottom of the essential spectrum. So from time to time, they appear a virtual level at this bottom, and when we make the window bigger, this virtual level turns into the eigenvalue. And L is critical if and only if they exist a non-zero function phi of n.
What does it mean critical?
Critical means that
The moment of birth of
yes. So when does it happen that we have a new eigenvalue for which L we should pass through to get this new eigenvalue? So it should be so that for such L, I should solve the boundary value problem. Here I have exactly 1 as a spectral parameter, and this one is the bottom of the essential spectrum. And this function phi of n, it should behave at infinity as follows. It should be square root of 2, square root of pi, sine x2, plus some exponentially small term. And this phi n, it's either odd or even with respect to x1. So here we shall have either the same behavior or with minus. So the virtual level is described by the existence of a non-zero solution to such boundary value problem. Once we have it, we shall get immediately one more new eigenvalue. It's possible to show that for each Ln, there is just one function phi n, that it's indeed virtual level and not an embedded eigenvalue in the sense that this coefficient here is non-zero. This phi n is not an eigenvalue, it's just bounded. And the question was, what can we say about the eigenvalue emerging from the essential spectrum once we have such situation? So now I'm speaking about.
Do you know the asymptotics of ln large n?
I know some. Actually, no, I don't know. And actually, we discussed this question, this issue with Sergei Alexandrovich Nazarov. And after he smoked a couple of, not couple, maybe three or four times. And then we decided that we both know how to do it. Actually, it's possible to do. This is quite simple. But it's possible to find the asymptotics for this Ln when it goes to infinity. And also from the very early results by Pavel Lekson with Korfos, it's also possible to get some quite nice bounds, to get some bounds for Ln from above and below the bracketing.
Will it be some power of n?
The idea is simple, that you add here additional boundary, put here Neumann or Dirichlet, and the same here. Then you can solve the eigenvalue problem in each box, and then you play with the minimax principle. it's possible to get the bounds for the eigenvalues, and this is actually means that you also get the bounds for this ln. And right now, so this is the result. It's our joint paper with Pavel Exner and Rustem Gadilshin and me. And then later I also published an independent paper in Сборник Mathematics. I guess it was 15 years ago when I was much younger. And so here we actually should do the same. So in order to study this effect, we should first understand the behavior of a resolvent of a free O operator. So we should, yes, of the free operator. So actually we should solve the following boundary condition. So here we have a boundary value problem. So we have here such boundary conditions. Then we write here u. Then we write here 1 minus k squared of u plus f. And the question is, what can we say about the solution of this equation? And the problem is that we don't have an explicit formula as for 1D case as we had here, like this, for the solution of this problem. Of course, at infinity we can make the separation of variables. But what to do with this Neumann window? So we cannot solve it explicitly. We should study it somehow in a different way. And here there is one more technique which is due to Maida, and it was also somewhere in 70s, maybe even earlier. The idea is how to make the meromorphic continuation for various operators in unbounded domains if we have something localized in the middle. For instance, we have an entire space, and for the Laplacian in the entire space, you can write explicit formula for its resolvent as it was in 1D case. And then just imagine that in the middle of a space, you add some potential. Then, of course, this which is localized. How to find then, so what can we say then about this resolvent? Of course, this explicit formula don't work anymore, but this technique says that actually it will be the same. Just up to some operator with just up to some equation with operator. The same it will be in the following sense. Just forget about this Neumann window. Think about the infinity of these outlets. Of course, we can solve this equation explicitly, right, at infinity. And then from this solution, we shall see that the resolvent behaves with respect to k as 1 over k. It's this 1 over k will appear at the first transversal sign. And this technique says how to prove rigorously that the behavior of a resolvent will be the same once we add something in the middle for instance window. The idea of this technique is as follows, that first we forget about the window. We consider the same equation just in the strip. And in the middle, we have one more boundary with the first boundary condition. And this will be V. This will be not U, this will be V. Actually, these are two boundary value problems which are very similar. It's one on this half strip, this one in the other. And then the function V can be found explicitly via separation of variables. Here I shall have like this. And if this is P plus, then I shall have here P plus, f of t, and here I should have some kernel which depends on m and on k, and this kernel is like, so it's written explicitly. It's equals to a form m квадрат. Нет. Разделение там переменных просто. Сейчас я выпишу ядра. It's just a separation of variables. Так. And also sines mt2 sin mx2. So you just take here a basis of sines, make a separation of variables, and then you solve the differential equations in this direction. What you get is exactly this formula. And we see here that as m equals to 1, so this one is 0, and we shall get here a pole 1 over k. But this pole will be cancelled since we have here two different exponents. So it means that if this will be denoted as 1 over k, action, and say it will be some function j here. Actually on j. So this operator is holomorphic in k. Because we can have here pole, but since we have added here one more boundary condition, then this pole is killed exactly due to this condition. So this is just a first step. So I want to solve such two boundary value problems. I can do it. Then I do the following. When I take a box with this Neumann window, here I have D recollect, and here I have equation of this form. Here W0, 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 dW with respect to x2 is 0, and here I just say that it equals to V. I just want to look at such to one more boundary value problem. The Laplacian of V is defined everywhere except for this middle. And this is why to have here a function from L2, I just say that I calculated separately in this part and in that one. And I don't care about any jumps on this line since it's a function from L2. I just don't care about this line. Another way will be to express the Laplacian of V from the equation for V. It's actually the same function V plus J. Okay? Then I just know that this boundary value problem is uniquely solvable, and it will be some operator actually acting on V, but V is a function of J. So it's an operator of J. So actually it will be also some linear operator from acting on J. And it will be again holomorphic in K, since there is no dependence on K in this problem. So this property comes from the same property of A1. And the third step, actually, it's almost the final one. I say that now I seek the solution to my problem as a, just to have, as the following expression, where chi is a cutoff function. So the graph of chi looks like this. It's here it's 1. So here it's 1 when it goes to 0, and when it's 0, 0, 0, 0, 0, and then it's again 1. So I just say that I have two functions. This one behaves nice at infinity. This function ensures so this function is responsible for the presence of this Neumann window. So I just make an interpolation of these two functions via some cutoff function, and just say that I want to find a solution to my problem in the following form. Why not? Let's try to do it. So here I also had an arbitrary function j. So then I want to find a j in such a way that this expression will solve my problem. This is the third step. And right from this formula, I get immediately that I know the behavior of this function at infinity. Since the cutoff function looks like this, then in this area, this one is absent, and I have here only W, and it gives the needed Neumann boundary condition. So the only thing actually which I should take is the equation. So such form gives me immediately the behavior at infinity and all boundary conditions. And I just assume that chi depends only on x1. So if I substitute this expression here, then employ the equation for this one, what I get finally is that j plus some operator A3 of kj equals to f, where A3 is some operator.
One-dimensional equation, right? One-dimensional.
No, this is an equation in L2, and if we denote this box by omega, this one, it will be an equation in L2 omega. So A3 is some operator acting in L2 on this box, and
You have to get an equation for chi, right?
no. Chi is some fixed function. So here I just choose some j. When I do all this thing, when I say I want to have a solution to my original problem in such form, and when I say that I want to choose j in such a way to get this solution, then the only thing I should check is the equation, and once I substitute this ansatz into this equation, then the final expression can be written like this. So this will be A3 looks as follows. It will be minus W2 minus V chi prime W2 minus V. It's like this. So once I substitute this expression into the Laplacian, they will be the terms when the Laplacian comes to W and V, then it's fine. And then they will be also mixed terms. So all these mixed terms are like the case when the second derivatives will fall on chi, or when one derivative is here and one is here. So all these terms are inside A3. Подставим вот. К G, конечно, к G. Функция W это через A2G, а V это вот это вот. То есть правильно надо подставить сюда, конечно, A2, ну и так далее. Okay. So this is the explicit formula for this A3. And now I have derivative of chi only. And this function are non-zero only in these subsets, right? Because outside they are zero. And now the main point is the following one. So in this subset, V, this function V, is an element of W22, right, on these subsets. And W is also an element of W22. Right? Just because of the usual regularity. But here I have only up to the first derivatives. It means that this operator, so when we map J into this expression, so this is an element of W22, this is an element of W21, 1 since I get one derivatives. And due to the compact embedding of W1 into L2, the operator A3 becomes compact as an operator in L2. So as an operator from L2 into W2, it is bounded because this one from W2 2, I take just one derivative. So A3 from L2 is bounded. And this is why A3 from L2 into L2 is compact. So what I have here is the operator is 1 plus A3 of K, JF. And this operator is compact, and it's holomorphic in K. Then it's known, this is a general theory, that the inverse of this operator, which I actually need, is meromorphic in K. This is a general thing. And if it's meromorphic in K, it has a pole at 0. Then there is extra maybe 3 pages of calculations which shows that this is a simple pole. And then I say that J is approximately as 1 over K, and here some function, say some function J0, and some functional on F. So finally, from here, I get the J has a simple pole in K. And then from this J, now I recover all this technique, the solution to U, the solution U to this boundary value problem. And finally, I get that it also has a simple pole. And this is actually the way how the meromorphic continuation can be constructed. And this technique is very powerful, actually, when dealing with all this stuff about about the emergent eigenvalues and resonances. It seems that I used it maybe in at least in 90% of my works, because you always have something localized, and you need to make the meromorphic continuation, and this is the usual way how to do it. Okay, and then actually we have again a simple pole. And then we have a perturbation, which is just a little bit shifting of this ln plus epsilon. And then actually we do the same thing as we did for the 1D operator, since we have here everything. We have a pole of a free resolvent, and we have a perturbation. Then the rest is just the machinery, which also gives the results. And it says that I have just one eigenvalue, and there is an asymptotic for this eigenvalue.